Okay, hi everyone. This is going to be a lesson on trig functions of angles. And if you watched the last video, you know that we already did trig functions of angles. But in that lesson, all of the angles were restricted to being in a right triangle. And in this lesson, we're going to break free of that mold and we're going to look at angles more generally. Okay, so let's go ahead and get started. So, trig functions of angles. I'll start by writing something that I just said. In the previous lesson, all angles theta that we were looking at, we were kind of labeling an angle of interest as the Greek letter theta. I'll remind you that that's what that is. All of them were less than 90 degrees. We had pictures that tended to look something like this, and there's an angle that we're interested in called theta. Now, how do I know that it was less than 90 degrees? If you have a right triangle and you have that rule that all three angles must add up to 180, then this has to be less than 90. You can't have a 90-degree angle in a triangle and have another 90-degree angle in a triangle, because that would already get you to 180. So all three of them have to add up to 180, which means this is less than 90. This could be 89 degrees, right? It could be very close to 90. The picture wouldn't look quite like this. Anyway, all the ones we looked at were less than 90, and we have a name for this. These are called acute angles. And right triangles only have these and one 90-degree angle. Other triangles, meaning not right triangles, could be. Have we drawn any triangles in this class that were not right triangles? Well, you could have something like this. And maybe the angle that we're interested in is this one. And that angle looks like it's larger than 90 degrees. So this is theta is greater than 90 degrees, and it is called an obtuse angle. So right triangles do not have obtuse angles. In fact, I'm going to label that this over here was a right triangle, and this over here could be called an obtuse triangle. An obtuse triangle is just a triangle that has an obtuse angle in it. Do you think a triangle could have more than one obtuse angle? Well, no, because you, again, wouldn't be following the rule that all three angles have to add up to 180. So these are kind of the two depictions of triangles that we're going to be the most interested in for this class. Now, let's get more general, and when I say more general, I mean I want to talk about angles not just in the context of triangles, but just angles. So let's let theta be an angle in standard position. We know what that means. And let x comma y be a point on the terminal side. By the way, when we say the terminal side, we mean the terminal ray. You know, technically we said that there are two rays that make up an angle, so you can call it the terminal ray or the terminal side. One picture of what this might look like is, well, it's in standard position. So that means that the vertex is at the origin, or I guess I could just say the origin is at 0, 0. And it's the vertex of this ray, and it's also the vertex of this ray. And this is an angle theta. How about I zoom in on this? All right, let theta be an angle in standard position, and let x comma y be a point on the terminal side. So the terminal one is over here. So let's say this is the point x comma y. So in this picture, we have the point 0, comma 0 and the point x comma y. I'm going to label some more things on this picture. I'll grab another colored pen here. I'm going to label the distance from 0, 0 to xy, and I'm going to call it lowercase r. All right? That's the length of that line segment. Another thing I want to show you is you might look at this and say, we could form an obtuse triangle. Like if you put a point on the initial ray, call it something else, and if you connected the 3 points, you would get an obtuse triangle that kind of looks like this one up here. There's something else we could do. What if we say, this is part of the x-axis, right? So what if we extend this a little further left and drop a line down from x comma y? You could actually get a right triangle. And that right triangle might help us in some way. So I'm going to zoom out and write some stuff to the side. By the distance formula, the distance from the origin (0, 0) to the point x comma y is, well, I labeled that distance as r, so let's call it r. R equals, from the distance formula, think about what the distance formula would say between these 2 points. X minus 0, y minus 0. We don't even need to write the minus zeros. You can just make it nice and simple when one of the points is the origin. All right, now, in the little right triangle that I drew, what are the side lengths of my little right triangle? I don't think I want to write more things on this because it's getting to be where I'm writing too much on this picture and it's gonna get confusing. But just like, what's this side length here? The bottom side length of this right triangle. It would be x, right? And what's the side length here? This would be y. And I'm talking about this length would be positive x, because a length can't be negative, and this length would be positive y. So we have a right triangle with side lengths x, y, and r. It's a right angle. Okay, so we know lots of things about right triangles. Anyway, we can define the trig functions of theta. Now, in the previous lesson, and the one before it, I guess, we've been talking about angles, and the previous lesson talked about the trigonometric ratios, and we looked at them in terms of, opposite over adjacent and things like that. And now, this is going to be more general. This is going to be for any angle theta, which might be less than 90 degrees. It might be equal to 90 degrees. It might be greater than 90 degrees. And we define it to be the following. We have 6 of them. We could say that sine of theta is y over r. Cosine of theta is x over r. Tangent of theta is... Let me start by saying, like, usually we expect sine and cosine. When we talk about the unit circle, we said sine of theta was y, or I guess we called it t back then. When we talked about the unit circle, we said sine of t is y, cosine of t is x. And that was fine for the unit circle, which had a radius of 1. But now we have something where the radius, or r if you want to call it that, could be greater than 1 or less than 1. So we have to divide by it. It's kind of a scaling factor. It's like the unit circle scaled up or down. You could even imagine the unit circle being here, right? I said I wasn't going to add to this picture, but you can imagine this whole thing taking place in a circle if you want, and then maybe that helps you see why we call it r, and r is the radius. So r is the scaling factor, so we have to factor that in. Tangent is still y over x, and the other ones are still the reciprocals of these first 3. So we could say cosecant is r over y, cosine has a reciprocal of secant of theta, which is r over x, and tangent has a reciprocal that's cotangent, which is x over y. And I kind of implied this above, but I'm going to write this down for our notes. You can think of r as radius for the unit circle, r equals 1. So everything that we said about trig functions in regard to the unit circle it's still consistent with what we're doing now. It's just that that's the special case where r is 1. And if r is 1, we get the familiar things we're used to, like sine equals y, cosine equals x, cosecant is 1 over y, and so on. So this is consistent with that, but now we might have something that's not just the unit circle. Now, if you had an angle, or maybe the angle is found within a triangle, for example, or maybe the angle is just given to you as an angle. If you wanted to find the trigonometric functions of theta, you might need to determine what r is. So how do you find out what r is if it's not given to you? Well, if r is not given to you, you might need to use this formula to find it. So let's circle this formula. If we know x and y, we can use this formula to find r. And then we know all the pieces we need to find all 6 trigonometric functions of theta. I guess you could say there could also be a problem where maybe r is given, maybe x or y might not be. Either way, you could use this. Doesn't this look like this comes from the Pythagorean theorem? I said this came from the distance formula, but, you know, if the side lengths of this little right triangle are x, y, and r, it seems like x squared plus y squared equals r squared, so doesn't it seem like the Pythagorean theorem? Well, it turns out that the distance formula and the Pythagorean theorem are very closely related. When you talk about right triangles, really it's the same thing. All right, let's do a problem. We haven't done any problems yet. So I'll do this first one. This is going to say, given the following triangle, find cosine of theta, and it's going to give a picture of a triangle. I'll do this one. Well, this looks like an obtuse triangle. Remember, a triangle has 3 sides and 3 angles. This is going to tell us the vertices It's going to tell us the coordinates of them. Okay, something had to be labeled theta if we're going to find cosine of theta. So we want to find cosine of this angle. We don't even know what this angle is in degrees or radians, but we want to find cosine of it. So that's all we're given. I'll show you how we can do this. You could think about it on your own if you'd like, but I'm fine with just showing you this one. How about this? I drew a dividing line here because I want to draw a second copy of this that we can add some scratch work to the picture without ruining the original picture. So if this over here is 6, 0, you know, you could overlay this whole thing onto the XY plane and do that if you want, but here's -4, 4. You know how in the discussion just a few minutes ago we said we let x comma y be a point on the terminal ray? Well, the angle that we're talking about here, remember, we think of angles as like a rotation from this initial ray onto this secondary ray. So it's going in this direction, the rotation. We rotated by this amount. So this is the terminal ray. It said let x comma y be a point on the terminal ray. We have a point on the terminal ray, so let's think of this as x, and let's think of this as y. All right, and let's label this r to agree with that previous picture that we drew. All right, now x is -4, y is 4. What is r? Do we need r? Well, think about this. Cosine of theta is equal to x over r. So yes, I think we do need r. We know x, we know y. We can find r using this little formula. Okay. -4 squared is 16. +4 squared is 16. So this is 16 plus 16 is 32. We'll see if we could simplify that at all. The thing I notice about the square root of 32 is that it is 16 times 2. And I know the square root of 16 is 4. So this is 4 times the square root of 2. All right, now we've got our x, our y, our r. In fact, if we have x, y, and r, we could find all 6 trig functions if we wanted. This problem's only asking us for one of them, but we could find all of them, right? They all use x, y, and r. All right, it wants cosine. Let's do this. X is -4. R is 4 root 2. And that's the answer, but we'd like to, fix it up and simplify it. We have 4 over 4, so let's first do something about the 4 over 4. 4 over 4 is 1. And then we don't really like to have a square root in the denominator, so let's multiply by root 2 over root 2. We did that a couple of times in the last lesson. And what we're going to wind up with is negative square root of 2 over 2. Hey, that seems like a familiar number that shows up in trigonometry. The square root of 2 over 2. In fact, I would even go as far as to say, based on this answer, I think I know what theta is. I think I know what angle that is. But that's kind of a topic for the next lesson. Once you know this answer, can you figure out what theta is? We answered this problem, though. It just wanted cosine of theta. I'll show you another type of problem. I'll do this one also. I guess I didn't really need to draw 2 pictures of that triangle. We didn't really add all that much to it. All right, different type of problem. If tangent of theta equals 2/3 and theta is in quadrant 3, Find cosine of theta. Huh, that's interesting. It's not giving us a triangle. It's not even drawing an angle for us. It's telling us something about tangent of theta, and it wants us to find cosine of theta, and something about the quadrant. Maybe that might turn out to be important. So I'm going to talk us through this because this is a different type of problem. Let's say we are given that tan of theta, which we know tan of theta is supposed to be y over x, it is 2 over 3. Okay. Before we go any further, I have something for you to think about. Does this mean that y has to equal 2 and x has to equal 3? Y over x is 2 over 3. Does y have to equal 2? Does x have to equal 3? Well, no, not necessarily, right? Y might equal 4 and x might equal 6. 4 over 6 does equal 2 over 3. So when you see something like this, a fraction equals a fraction, you can't automatically say, therefore, y is 2. We don't know that. Y might be 20, and x might be 30. So don't assume that y is 2. All right, that's okay. We'll continue. What we said here is true, though. We are given this equals this equals this. All right, I have some things to tell you. Except for sine, S-I-G-N, except for sine, the values of trig functions of any angle theta are the same as those of an acute angle theta with a bar over it. We could just pronounce that theta bar. This is called a reference angle. If this sounds vaguely familiar, this is the same idea as a reference number, which was T bar from our earlier lessons. I'm going to put that in parentheses. Remember when we talked about reference numbers and T bar and how it could help you figure out a trig function of a T value? Well, now we might want to find a trig function of a theta value, and we're thinking of it in terms of angles, but it's a similar idea. Let me tell you what this means. This means we can, step 1, draw an angle theta bar in quadrant 1. Why am I saying quadrant 1? Well, it's because if you have an acute angle and it's in standard position, it's going to be pointing in quadrant 1. If it's acute and it's in standard position, it's going to point in quadrant 1. Okay? Number 2, we can get an answer. Basically the answer is for theta bar. And then step 3, adjust the sign, S-I-G-N, to be appropriate for the quadrant given in the problem. For example, 3. This problem above says quadrant 3. We're still going to work on this problem. I just had a lot to say about it in between. So let's work on solving this. Now, I said a moment ago that just because y over x equals 2 over 3, it doesn't mean that y has to equal 2. It doesn't mean that x has to equal 3, right? It just means that the ratio of y over x is 2 over 3. But for this process, when we draw an angle in quadrant 1, I am going to use the 2 and the 3 because I know they're going to give me the correct ratio. So instead of doing like 20 and 30 or something like that, I am going to draw this with a 2 and a 3. Let's draw an angle in standard position in quadrant 1 where y is 2 and x is 3. Let's just start with that. And I guess what I'm saying is if you want to make this 4 and 6 or 20 and 30 or 2 million and 3 million, that would also work out. It's going to work out the same. So we might as well just use the simpler numbers. What angle is this? This is our reference angle. Okay, I know from the problem, the problem says theta is in quadrant 3. This picture is pointing towards quadrant 1, right? If this is the origin, 0, 0, imagine the x-axis and the y-axis. This whole thing is taking place in quadrant 1. So this is not theta, but we can use this to help us find theta. Let's also label r. R is kind of the hypotenuse of this. Now, this has tangent of theta bar equals y over x equals 2/3. And we want to know cosine of theta bar. What is cosine supposed to be? Cosine is supposed to be x over r. And we want to find it. Again, we need to find r. R is the square root of x squared plus y squared. In a lot of the problems in this section, you'll need to find it. We use this x and this y. So square root of 3 squared plus 2 squared equals the square root of 13. Can we simplify square root of 13? I don't think so. I think square root of 13 we have to leave as is. That's okay. We'll leave it like that. So, cosine of theta bar, I was going to write is. I've got a better idea. Instead of writing the word is, why don't I just put an equal sign? Right? Equal sign. X over r. So 3 over the square root of 13. Again, multiply by the square root of 13 over square root of 13. This is going to give us 3 root 13 over 13. Let's take a quick look to see if we could simplify it. 3 over 13. Does that cancel in any way? No, I think we need to leave it like this. Is this the answer to the question? Remember, the original question told us to find cosine of theta. All right, so you saw the problem. If you wrote it down, scroll up in your notes and look at the original problem. Let's think about quadrants, right? Quadrant 1, quadrant 2, quadrant 3, quadrant 4. They go in this order. I said that everything here has been taking place in quadrant 1, but this problem says theta is supposed to live in quadrant 3. We need to do step 3 of the process. We need to adjust the sign to be appropriate for the quadrant given in the problem. This is the answer, but does it need a plus in front of it, or does it need a minus in front of it? I'm going to say, in this case, theta is in quadrant 3 where cosine is, let me ask you, cosine of something in this quadrant, do you think it's positive or do you think it's negative? I'm going to say negative. I'm saying negative because you can use everything that we know about the unit circle, everything we know about sine and cosine so far, right? Cosine is like x coordinates on the unit circle, which are negative when you're over here in quadrants 2 or 3, positive when you're in quadrants 1 and 4. So all the way over here, cosine is negative. So the answer for cosine theta is the answer we found for the reference angle, except with a minus sign in front. And that's the correct answer. So that was a different kind of problem. It gave us something about, it said tangent theta equals 2/3, and it said theta is in quadrant 3. We wanted to find cosine of theta. We never actually found what theta is. Based on this answer, do you think we know what can we estimate what theta is? I would say not really, not by hand. That's hard to figure out what theta is because this is not a familiar number that we've seen in this class. It's not like square root of 2 over 2. This is negative 3 square root of 13 over 13. Well, it's some kind of angle pointing in quadrant 3. We can just leave it at that. I want to talk a little bit more about, so we answered the problem. Let's talk more about sines and quadrants. Okay, how did I know that cosine is negative in quadrant 3? How did I know cosine is negative in quadrant 3? Let's draw something here about quadrants. Here we'll label them on the inside, like quadrant 1, 2, 3, 4. They always go in this order. They kind of go in the same order that we're used to going around the unit circle, right? So you start with 1 here, and then you go counterclockwise, 2, 3, 4. I want to say that all points in quadrant 1 are always of the form positive, comma, positive, right? Because that includes points like 1, comma, 1, 2, comma, 3, 5, comma, 10. They're, it's always positive, comma, positive. And anything that lives in quadrant 2, any point that lives in quadrant 2 has a negative x value. So it's something negative, comma, something positive. Since I'm talking about x values and y values, I'm going to label these. This is basically my x, comma, y, my x, comma, y. In quadrant 3, both of them are negative. You think about what points you could find down there. What's down here? Negative 5, comma, negative 4, things like that. X is negative, y is negative, and in quadrant 4, you have a positive x value and a negative y value. This is not like a graph, this is not like a diagram that you need to memorize. This is something that you need to understand, right? You need to understand how the x-axis and y-axis give you positive or negative values depending on which quadrant you're in. So how did I know cosine was negative in quadrant 3? Well, let me write that. How did I know cosine is negative in quadrant 3? Well, cosine of theta is x over r, where I've got something to say about r. Where does r show up in this? Here's x and y, x and y, x and y. Where does r show up? Well, I'm going to say r is always positive. How do I know R is always positive? Because it's a distance, and it comes from this formula which must be greater than or equal to 0. You know, a formula like this, if you put in a positive or a negative value of y, it doesn't matter if x or y is positive or negative. Either way, when you square it, it becomes positive, right? A negative number squared becomes positive. Even if x and y are both negative, when you square it, it becomes positive. Square it becomes positive. Add them together. Take the square root. R is a distance. You get a positive answer. Now, this little formula, algebra tells us that this has to be greater than or equal to 0. But I could actually go a step further and say that it can't even be 0. I could just say greater than 0. I know it can't be 0 because if it were 0, we wouldn't really have an angle at all. Like, we need to go from the origin 0, 0, some distance to a point x comma y. That distance needs to be positive. All right, so in this little formula, cosine theta equals x over r, where r is always positive, it means that the sign, sign, is going to be determined by the numerator x. If the bottom's always positive, then x determines the sign. And I'll just say that in quadrant 3, x is negative. So cosine of theta is negative. All of this was kind of discussion stemming from that one problem, but you can use this kind of reasoning to figure out the appropriate sign for any problem like this. And it means that we can use reference angles to evaluate trig functions just like we did with reference numbers. So some of the problems that we see in this section are going to look like problems we did back then with reference numbers, except now we might talk about them in both degrees and radians. Back then, when we talked about them with reference numbers, back then we just thought of them as t-values. Now we understand that the t-values that we were looking at back then could be thought of as radians. All right, we're going to move the page. I'll leave this for just a moment in case anybody's copying it. Okay, let's move this page away, make some room for some problems. So example, let's find, I'll do the first one. There's going to be 3 parts, and I think I'll do the first part. So we're going to find part A, sine of 240 degrees. Part B, cotangent of 390 degrees. And part C, secant of negative pi over 4. So let me do the first part for us and show you how reference angles are going to help. You see that part A and B are in degrees. Part C doesn't say degrees or radians, and that means it's implied that it's radians. All right, part A. You know how in previous lessons, a lot of times we did a scratch work unit circle? Well, this time we don't need a unit circle, but we could still draw a scratch work picture of this angle. Now, I know that if we went all the way around, we would be going 360 degrees. All the way around is 360. That means going halfway around is 180. We want to go 240. So we want to go 180 degrees plus 60 more. So I'm going to draw this to be 180 plus about 60 more. And that puts a ray pointed something like this. And I'm going to label what I wrote here. This is my 240 degrees. You see that? I'll zoom in. Now, what is my reference angle going to be? Just like in the previous lessons where we did reference numbers, my reference angle is basically going to be what gets me from here to the x-axis. What is this angle here? How big is this angle? That's right, this is theta bar. It is an acute angle, right? Theta bar looks like it's less than 90 degrees. So I'm going to zoom out and say that for part A, my reference angle, theta bar, it's 60 degrees. How do I know it's 60? Because when I drew this, I was thinking 240 degrees would go 180 plus another 60. That's my 60. So if we're following this sort of three-step process of using reference angles, step one was to draw an angle in quadrant one. We didn't really draw this in quadrant one, but we identified what the angle is, so maybe that's good enough. Step two says to get an answer for theta bar. So we want sine of theta. Let's find sine of theta bar. Sine of 60 degrees. I still think at this point in the course, we might be more familiar with radians. So if you'd like, you could convert the 60 degrees to radians. We talked about how to do that. You'll find that it is pi over 3. And if I asked you what is sine of pi over 3, that's something that we've been able to answer for a couple of weeks now. Sine of pi over 3, it's one of the common values. It's the square root of 3 over 2. So my answer for sine 240 degrees is going to be square root of 3 over 2. I just need to figure out if it needs a plus in front of it or a minus in front of it. I'm going to say sine is negative in quadrant 3. Why am I saying quadrant 3? This problem just said sine of 240 degrees. It didn't say what quadrant we were in. I'm saying quadrant 3 because I can tell from the picture that we're in quadrant 3 and that sine of this angle must be negative. So, because the y value is negative. So the answer then is that sine of 240 degrees is the answer that we found above, but we have to put a minus sign in front of it. Negative square root of 3 over 2, and we answered the question. That's my answer. Don't put a box around the other one. The other one was sort of a stepping stone that we used along the way, but this is the actual answer. All right, so I'd like you to try part B and C on your own. So I would encourage you to pause the video here and take a minute to try them. So I think for each of these, B and C, I think I'm going to draw a similar picture like I did here. 390 degrees, and it's cotangent. Let's just start by figuring out what 390 degrees looks like. 360 would go all the way around. So 390 is going to go all the way around. Here, we'll zoom in. Go all the way around once. We've gone 360 degrees, and then we go plus another 30 to get to a grand total of 390. So we're pointed in this direction. (390°). That means that my reference angle is going to be the angle going from that ray to the x-axis. We'll say that's theta bar. Didn't I say we went 360 degrees plus another 30? Well, it turns out that that means that a good reference angle would be 30 degrees. So let's find cotangent of 30 degrees. And then our final answer to the problem is going to be this, but then we'll have to figure out if there's a plus or minus in front. So, do we know what cotangent of 30 degrees is? One thing you could do is you could turn this into 1 over tangent. Maybe that's easier. And then say tangent is more familiar to us. Maybe we know this one. So do some scratch work off to the side if you need to find tangent of 30 degrees. Convert it to radians if you want, but you should get square root of 3 over 3. Which means that this is really, 1 over this fraction. Let's, instead of dividing by a fraction, we can multiply by the reciprocal. So this is 3 over the square root of 3. Again, I don't like to have a square root in the denominator, so we multiply by root 3 over 3. It gets us 3 square root of 3 over root 3 times root 3 is 3. So look at this. Look at how this simplifies. It equals the square root of 3. It's not even a fraction. Remember, don't circle it yet. We need to figure out, because that was just for the reference angle, so we need to get back to the actual angle. Cotangent of theta, not theta bar, but cotangent of theta is x over y. Is it positive or negative? Well, in quadrant 1, x is positive and y is positive, right? In quadrant 1, x is positive, y is positive. So when I do a positive over a positive, we get a positive answer. So cotangent of 390 degrees is the answer that we found, and it is positive. So square root of 3. And now I'll put a box around it because we checked. We know that positive is correct. All right, so you can do things. You can do things like cotangent of 390 degrees. The next one asked you to do secant of negative pi over 4, so we get something negative involved. Let's draw a quick picture of it. Since this one's in radians, we could actually say it might feel even easier at this point, because we know negative means to go clockwise. We know pi over 4 means we're going in this direction. Okay, here, I'll draw this. The reference angle. You know how we said that a reference angle is supposed to be acute? A reference angle is in quadrant 1. In this case, we can use positive pi over 4, because you can think of that as being sort of the positive angle distance that gets you from here to the x-axis. Like that's an angle of pi over 4. So we want secant. Let's do secant of pi over 4. We'll find this answer, and then we'll figure out if we're supposed to be positive or negative. So this is 1 over cosine of pi over 4, which is 1 over square root of 2 over 2. Try to simplify this. Well, this is 2 over the square root of 2. And if you multiply by root 2 over root 2, this simplifies to the square root of 2. Now, we are in quadrant 4. I can tell from the picture, right, that we're in quadrant 4. Quad 4, where secant is, what do you think? Positive or negative? Secant is 1 over cosine. I guess I shouldn't say 1 over cosine. I guess, I should say it's r over x. In terms of the unit circle, it was 1 over x. But in terms more generally, it's r over x, where r is always positive. So really, the sign, sign, is going to be determined by the sign of x. Well, x is positive in this quadrant, so secant is positive in this quadrant. So secant of negative pi over 4 is the answer that we found, and it is positive. Cool. All right, so we did all three. So that's one type of problem that you could see, asking you what's sine of 240 degrees, what's cotangent of 390 degrees. You could have a question that's in degrees or radians, and we can now do trig functions of any angle. It could be positive, negative, it could be greater than 360 degrees. Oh, I guess I should clarify that, some of them could be trickier than others. We were able to do this because the reference angles that we got were things that we were able to evaluate. Sine of 60 degrees, we are able to do that. Tangent of 30 degrees, we can do that as long as like one of these sort of common values shows up. But if a question were to ask you, what is sine of 17 degrees or something weird like that, those are problems that we're not really able to solve yet. So I guess I shouldn't really say that we can do a trig function of any angle by hand. But we can certainly do trig functions of a lot of angles. All right, we've got another thing to talk about here. Another thing for this section. We want to talk about areas of triangles. That's something we haven't talked about yet. You might know some things about area of triangles. If you had a triangle, and I'm going to try to draw one that is, maybe it's a right triangle or maybe it's not. Just in general, some kind of triangle here. You know that maybe we could call this the base, and we could call this the height. And if we knew the area, if we knew the base and if we knew the height, then we could say that the area of the triangle is 1/2 times the base times the height. That's a general formula for the area of a triangle that you might have learned a long time ago. And it's still true for us. Now, there's nothing wrong with that formula, except what if we aren't given the base and height? What if we're given other things, other information about the triangle? I'm especially concerned about the height. Are we really going to be given that height? It's not one of the side lengths of the triangle. The base, at least the base, is one of the side lengths. But the height is like this weird, mysterious other thing. So let's draw a picture of a triangle here. It doesn't have to be the same one. And let's label, how do we want to do this? I'm going to label this entire thing down here to be A. And I'm going to label this side length to be B. And I'm going to say this angle right here, the angle made from A and B, I'm going to call it theta. So what is the height? Can we figure out the height of this triangle? How about this? How about we take the point that's at the highest point and we drop a vertical line segment until it touches A. And we call that the height. I'm going to call it H. So something that you might notice is if we truly dropped that straight down, this right here is a right angle. Okay? The overall triangle that I drew looks like it might be a right angle up there, or it might not. But this right here has to be a right angle if we dropped this straight down and if A was the sort of flat bottom of the triangle. So can we figure out the height? That's my question for you. Because let's say I look at this triangle and I say, I know what the base is. The base is A. If I could figure out the height, then we could use the area formula. How about we use this right triangle that we formed, this triangle inside a triangle, and we try to figure out H. Now, we're kind of assuming that maybe we know what A is, and maybe we know what B is, and maybe we know what theta is. That H, the height, is kind of the weird part. That's the part we don't know. We could maybe use one of the trigonometric ratios with this right triangle. I guess if you just looked at this right triangle, B would be the hypotenuse. And H would be the opposite side length from theta. So what trig ratio uses the opposite side length and the hypotenuse? It would be sine. Sine is going to be H over B. So H is B times sine. So what I'm saying is we could find the height of the triangle in terms of other pieces of information that we might be more likely to be given. It's more likely that we're going to be given B and theta or sine of theta. And, if we know those things, then we can find the height. So the area formula, what does it look like then? How about I rewrite this formula in terms of A and B, and instead of writing H, we could write B sine theta. So we still have the 1/2 out front. The base is A, the height is B sine theta. So we just found a new area formula for the area of a triangle. The thing that's nice about this area formula, I'm going to put a star next to it. The thing that's nice about this version of the formula, A times B times sine theta, is that it doesn't assume that we know the height. All right, it's based more on side lengths and angles. You might look at this and you might say, well, okay, that's fine if the triangle looks like this. We were able to drop this down and make a right triangle. But what if the triangle looked like something else? Would this formula still work? So I'm going to draw one other case to try to convince you that this formula actually does work, even if a triangle looks different. So what if I had a triangle like this? And this is A, this is B. Can we still do the same kind of trick to figure out the area of this? Can I use that formula? Does it seem valid to do that? Here's the highest point on the triangle. So what if I try to drop down a line segment until it reaches the bottom? Well, really what I want to do is I want to reach the lowest point on the triangle. So let's extend this a little bit. All right, that's what I want to do. And this does make a right triangle here. And we'll call this the height. That's the height of the triangle. We'll call that h. Now, it seems weird to use sine of theta when theta is not even in this right triangle, this little right triangle that we formed. But guess what? Guess what is in this right triangle? Theta bar. That would be the reference angle for theta. And sine of theta bar is h over b. So h is b times sine theta bar. So does this mean that we need to have something that basically looks like that above formula, but instead of theta, it says theta bar? Well, we could do that. We could. But in fact, I claim that h equals b sine theta also works. The reason why we can change the theta bar to a theta is because if this point right here is at the origin, then how do I put this? I want to say that in this picture, theta looks like it's greater than 90 degrees, right? Let's say theta, right now theta is not in standard position. I guess maybe that's what's bugging me. Theta in standard position. We would flip this picture around, I guess, but theta in standard position would go, here's the origin, and maybe it goes like this. My point that I'm trying to make is that this is in quadrant 2, right? So the reason why this works is because theta is in quadrant 2, and theta bar is in quadrant 1, where sine is positive in both. Does that make sense? When we use a reference angle, the only thing that could possibly change is maybe there winds up being a minus sign in front of it. But I'm saying that by this argument of quadrants, we could actually say that there's no minus sign that pops out. So sine of theta bar is equal to positive sine of theta. So the point of this is that h is still b sine theta, a is still a, the area is still going to use 1/2 base times height, so it's still the same formula that I wrote above. So what I'm trying to convince you of is that this formula, which I put 2 stars around, it works in general for triangles of all different shapes. All right, so result, let's write this to be clear about it. The area, A, of a triangle with sides of lengths A and B enclosing an angle theta is this formula. All right, all that matters is that has the 2 side lengths A and B. And the angle, theta, has to be the angle. I used the word enclosing. It has to be the angle formed by A and B. You see that in all of the pictures that I drew above. Look at where theta is and look at where A and B is. So theta is the angle formed or enclosed by. In some textbooks, instead of the word enclosing, they'll use the word including. So I'm telling you that in case you see that in like a homework problem. If it says, oh, here's a triangle with, a side of length 4 and a side of length 5, including an angle of 30 degrees. So if you see the word including, this is the same idea. A and B are the two sides forming that angle. So it's not just any two sides and an angle. It's the two sides surrounding the angle. Then you can use that formula. And theta can be in degrees or radians, either way. In fact, it'll probably be in degrees usually for these problems. So let me give you one of these to try. I'm going to ask you to find the area. We talked a lot about that. Let's actually have a problem. We'll give you a picture. It's going to look like, well, this might not be totally to scale because I already drew that at a certain angle, but that's okay. It's going to be close enough. I'm going to label 120 degrees, 3 centimeters, 10 centimeters. And I'd like you to pause the video and give this a try. All right, let me zoom out because we're going to write some things around this. So we want to find this area. We're going to use that formula. We know we're going to use that formula. We definitely have two side lengths enclosing an angle. So the solution is going to use the formula A equals 1/2 AB sine theta, where we understand what A is and what B is. By the way, does it matter which one of these we call A and which one of these we call B? It doesn't really matter because they're going to get multiplied by each other either way. Whether we do 10 times 3 or 3 times 10, doesn't matter. Sine of 120 degrees. What's 1/2 times 10 times 3? You should get 15. That's where we're at so far. Those side lengths are measured in centimeters, so at the very end of this problem, since we're doing an area, we're going to get some number, and then at the very end, I'm going to write centimeters squared. All right, do we know what sine of 120 degrees is? You might not know off the top of your head. I think we might prefer to think of it in terms of radians. It's optional whether you convert this to radians or not. If you can think in terms of degrees, that's fine. But we've been talking about t values and unit circle for so long that I think converting to radians might help us. And when I see sine of 2 pi over 3, you could even do a scratch work unit circle if you want and say, oh, where's 2 pi over 3? I know where pi over 2 is. I know where pi is. And then that might help you remember that 2 pi over 3 goes this far. We're looking for sine, which is the y-coordinate. So this is 15 times the square root of 3 over 2. All right. Let's look for, can we cancel anything? 15 over 2 doesn't really cancel at all. So let's write 15 square root of 3 over 2. And it's this many centimeters squared. That is the area of that triangle. By the way, did I use a reference angle in that problem? I guess I didn't really use a reference angle. I said sine of 120 degrees. I said I could figure out, what this equals. So I'll say, or use a reference angle if you prefer. You could say, here's the 120 degrees. So the reference angle that you would work with would be 60 degrees, and you would say sine of 60 degrees, and work with it that way if you prefer. And then you'd say, oh, well, sine of 60 degrees is the square root of 3 over 2. So sine of 120 degrees is the square root of 3 over 2. That's another way to approach the problem. Either way, you need to figure out what sine of 120 is. Let's do one more. Let's find the area. I'll draw a picture, and I'll give you a minute to think about it. Again, these pictures I draw by hand. They might not be perfectly to scale. It's okay. Close enough. We're going to say this is 45 degrees. This is 7, and this is 6. So it's not saying centimeters or inches or anything. So it's just 7 units and 6 units. All right, I'd like you to take a minute and try to answer that one. You can pause the video. All right, so we don't know the other angles, and we don't know the other side length, but we don't need them. We have two sides that are enclosing an angle, so we basically have A, B, and theta, and let's just use that formula. Let's say we want 1/2 AB sine 45 degrees. Well, I guess really we could say 1/2 times 6 times 7 times sine of 45 degrees. What's 1/2 times 6 times 7? Well, 6 times 7 is 42. What's sine of 45 degrees? Sine of 45 degrees, we know that that is the same as pi over 4 radians. So sine of 45 degrees is sine of pi over 4 radians. It is the square root of 2 over 2. We've basically got the answer, but we'll try to simplify it. 1/2 of 42 is 21. I get 21 square root of 2 over 2. Does anything else cancel? No, not really. Just leave it like that. And it's going to be this many, and we'll just say something like units squared, square units. Okay, so we're going to wrap up in a moment here, so I'll leave that for a second in case you're still copying it. All right, so we saw a few different types of problems in that section. We learned about doing trig functions of general angles. So, something like cotangent of 390 degrees, you know how to do that. Sine of 240 degrees, you can do that. So I could ask you a lot of trig questions now about degrees or radians. I could say, what is sine of negative 135 degrees? I could ask you, what is tangent of 210 degrees, right? And we can figure these out like we did with those example problems. You could also have a lot of triangle problems. In the previous lesson, we had some stuff about how to solve a triangle, and now we know how to do things involving the area of a triangle. And we did a couple of those problems. All right, so we're moving right along. We're covering lots of stuff here. That's a good place to stop. So hope everybody's doing well, and take care.